All right. So welcome. This is M1, the basics of robotics. And we have done unit 1 and 2 yesterday. And now we're doing 3 and 4. And unit 3 is really about problem solving and applying what we've learned yesterday to get the robot to move. And we're going to consider navigation. Mostly linear, because we haven't got any further yet, but that's fine. And then the next session is on passive attachments. And passive attachments are not added to robots just to make them look nice. Passive attachments are attached to robots to make them more functional. And so we will look at that afterwards. All right. So let's start with unit 3. And we are going to consider then problem solving. And before I kind of go over to the presentation, I just want to just kind of look here. So this is a robot. The robot's name is Mozart, by the way. But you can program the wheels to rotate, okay? And I think at the start, at the very outset of this lesson, you need to understand that if the motor rotates once, this wheel will rotate once, okay? And the distance that the robot will then travel is then the circumference of the wheel. Now, I know so maths and circumference of wheel is like a really calculation, but we make it easier for our learners to grasp the concept. And I often have a piece of, and now I'm looking for my piece of ribbon, and I do not see it here at the moment. Anyway, so yeah, I have a piece of ribbon, and then you just go around the wheel to say, then that is the wheel diameter or circumference, and then you will be able to have that as the distance that it's going to travel in one rotation. All right. So if you have a little wheel, then if you go around it, the circumference is maybe that much. But if you have a big wheel and you take the circumference of that, then it'll be that much. All right. So that is and to ensure that the learners really understand that if you have a smaller wheel and you do one rotation, you still do one rotation. You're just not going to go as far as having a larger wheel. Still one rotation, but your robot's going to go further. All right. Now I'm just asking Casper, why is Mfunzo's screen larger? Not sure where that's happening. Okay, never mind. I'm sure they will sort it out. So that is at the very basics. Why you need to understand that the circumference of the wheel will then determine the distance your robot is going to travel. Okay, so that's the first concept. The second concept is if you have a program, right, and you change the wheels, you're not going to have the same results, okay? Similarly, if you have a robot and you change the program, you're going to have different results, all right? So what we want at all times is we have a robot, we have programming, and in between, that's where you develop the 21st century skills of your learners. You want them to understand what they're doing. And I think robotics allows you a practical approach to see what is happening and what the solutions are. Okay, so there's my robot. I've explained the circumference of the wheel, and so there's a navigation issue here. If you can maybe start thinking about it, if you were, how would you program your robot to write your name? Okay, so if your name is, say, and I see Thomas has just joined us. So Thomas, T is easy. You make the robot go forward, and then it must turn, and then it must go forward that way, and then it must reverse that way. That's a T, okay? Casper will also be quite easy because you just have to make the robot turn in that direction. Obviously, you're going to attach a filter pen or a Koki pen to your robot, and then you can draw on it. But it's lots of fun trying to figure out, and so it's very easy to introduce big words like algorithms and circumference. What we really want to do is to encourage our learners to think a little bit and to maybe figure it out and let them see what happens. Okay, so let's quickly start the presentation on Unit 3 already. And you'll see, and I hope you'll just enjoy based on what you've already learned. Yesterday, we learned how to build a robot, okay? And we learned about the basics of programming. Now, we have to apply it, okay? Step by step. Okay, so and then you'll see as I explained in that overview document, in Unit 3, we kind of define navigation as the ability to move in its environment. Okay, so we've only done wheeled robots, so they are kind of moving easily. And so the robot navigation for a wheeled robot is a little bit more difficult, or a little bit more different, maybe to a robot that navigates under the sea, because then you're going to have to do fish-like movements, or a robot that navigates in the air. That's also different. And of course, a robot that navigates on Mars, that's a totally different kettle of fish. Right? So we're just doing robot navigation in our classrooms where we are working with our learners. Okay. And so at the moment, we don't have data. Okay. So we can't really say, well, where is the robot? Where's the robot going? However, when we start in M2, we're going to start adding sensors. And so then we'll get measurements from your environment to say there's an obstacle in front of you, or you're about to go down a cliff, or there's the color red on the road when you need to stop, or something like that. So then obviously your navigation will be cleverer, if there's such a word. Okay, and odometry is then odometry data is using the data that the robot has measured to make the robot intelligent. And I use intelligent very lightly. Okay, and then there's different robot techniques that we can use, or navigation techniques. It's just easy. It must be understood, though, that your robot must be autonomous. At this stage, we're not doing any remote control. Okay. And so if we have an autonomous robot, we need to know where it's going. Okay. So, and it's not like we can just press a button and stop it. So if you measure, say, from here to there, and it's 30 centimeters, and you program the robot to travel 30 centimeters, it's going to travel 30 centimeters, and that's about what it is. Okay, so that's autonomously. If you're on autonomous mode, you can't remote control it to say it must turn somewhere, or it must stop earlier, or anything like that. But autonomous is really, it behaves as you have programmed it to do. All right. Okay, so now we're going to come to problem solving, and there's always a number of steps, and it goes by many names. So there's the technology process, and there's all kinds of problem solving processes, but each one has always got a whole lot of steps. Okay, so you define the problem. We would know what the problem is, and you find possible solutions, and then you select the best one, and then you implement and you test it, and then you kind of go in this iterative loop. All right, and there are many problem solving skills that your learners need to develop. Okay. It doesn't always come that easily, and please don't assume you're going to start with the learners just solving problems. That is part of this process of the 21st century skills, of developing the skills to solve problems. All right. And things you can use is like brainstorming. I love using big pieces of paper and lots of Koki pens. Draw your solutions. Draw how you think it's going to be. All right. You should actually name the steps. Okay, so what are we doing now? Now we're defining the problem. Then then it's going to look for solutions. And then what are we going to do? So we're going to select the best one, and then we're going to implement it and test it, and we'll probably go around in the loop. So you need to guide your learners through the steps of problem solving. And please don't give them the answers. Please don't give them the answers. Okay. All right, so I've got some activities here. I've listed some activities here, which we're going to get to in the end. But how must the robot draw the first letter of your first name? How is it going to do that? All right, so then we think about that. We'll come back to it just now. How must the robot move in a square around a shoebox? So assuming you've got a square shoebox, then it's actually going to do 4 times exactly the same thing. Okay, and what is it doing? Well, so this is just another way also of problem solving, and it's one of my favorite ways of problem solving, is act it out. Let the learners dramatize it, without being drama queens, but let them walk it. Okay, so give half the learners the chance to be the robot, and the other half the learners are then the programmers, and then they must okay, so how would you walk around a box? How does the robot move? And then similarly, how does the robot move around a rectangle? So the rectangle, you've got a short side and a long side. So it'll go short, long, and then you must repeat it. Short, long, and then that's right. Okay, moving around a bucket is not that easy. You've got to keep turning around Although I must say some of my learners have gone a square around a round bucket, and they said, well, you didn't say it has to go in a circle. So I've added now, it must move in a circle around a box, around a bucket. Your learners are very clever. Okay. Okay, so this thing about problem solving, it does require skill. Okay, it is a skill. I know you can teach it, but I rather work to the realm of you develop it. Okay, and I can see that in the teams that I've been coaching, the problem solving skills are developed. They become enhanced. They become almost like expert mode in all these skills that they're developing. All right, so problem solving is right there, and it needs practice. And so here's my little disclaimer: it's not a textbook, in the textbook kind of answer. It never is. Okay. You can access building instructions, and you can access sample code, and you can ask any of us how to do it. And if you want to know how to design things, you ask Casper. And if you really have programming complexities, yeah, ask Sylvia. But after all that, there might not only be one correct answer. So especially you who are new to robotics, be kind to yourself, because there might be lots of correct answers. Okay, why do we use robotics to teach problem solving? Well, there's a lot in the literature. Okay, just to go back, I prefer to say we're going to use robotics to develop the skills of problem solving. So learners that do robotics are much more patient with themselves to solve a problem. Maybe I should write a paper on that. Okay. All right. So it's practical. You have to work together. You kind of, what is the glue? What is fixing? What is fitting what? You can't memorize a correct answer. There is no such thing. All right. But what you do have is you have an understanding of what the problem is. Okay. So you look at this and say, okay, so what is the problem? I'm going to give you a whole lot of problems now, and we're going to discuss. Okay. So how do you solve this? And it's always important. And I'm going back to books and paper. Write it down. Write down what you understand. What do you have to do? The robot has got to travel from here to there, and then it's got to fetch something. Or it's got to go from here to there, and then it's got to stop. Write it down. It's no use like just grabbing it from the sky and hoping to goodness it's correct. Okay, so whenever you start, and you have to start, that's one of the things, see where you are. Okay, where you are and where you're going. Okay, all right, so here we are. Where are we? We're here. We've got a robot. We can move, and we understand navigation. And I've put at the bottom there are lots of other robotics learning coming. So we can learn about touch sensors and ultrasonic sensors and all the wires and cables and variables. We're getting there. Okay. But for now, we're just going to make the robot move forward and move backwards. Okay. And at all times, we need to all of us, we need to understand very clearly what is given, what is known, what is required. Okay. And we're only doing navigation for wheeled robots. Let's just start with the simple stuff first. Okay. So here we go. So we have got a robot, and we know where the robot starts, and we know the robot ends, and now we've got to get some problem solving in between. This is a method or an approach that my friend Dr. Tanya Kopp presented when she was here in 2016, and it's just kind of like stuck. It's a good start, and it's a good way of, it's an active learning approach. Okay, and it says called thinking like an engineer, but thinking in a structured way. Okay, so first you sketch it. What do you need? And kids love drawing. Just draw it. It doesn't need to be so exact, but sketch it. And then what are the objects? What do you have to do? And then you've got a list. What are the variables? What are the things that you've got? And what are the equations? And I think it's important. Oops. Oh. And then to understand how do you manipulate it. Yes, there's maths involved. Okay. But if you introduce it as part of solving problems, I don't know, maths just triggers a whole lot of bad connotations. Okay, so let's go here. Now you're going to help me. We've got to move in a straight line. Okay, and we've got robots at start here and it stops here. Anybody want to help me? How do we know how to get the robot from there to there? Anybody want to unmute and kind of share some thinking? What are they thinking? Anybody?
If anybody, you can just raise your hand or unmute or use the chat area.
No? Okay, well, I'll start giving some examples, and then if you can interrupt me, you're more than welcome. Okay, so it doesn't say here. So the robot starts here, and it's got to travel this distance to there. Okay, it doesn't say where the robot's going forward or backwards. You notice that? And it doesn't say how fast it must go. You know, it's just go. It might take a long time to get there. Okay, so the robot, the wheels need to be programmed in rotations. But now you can't say go 4 rotations because it depends what wheels you've got. Okay, so the robot wheels, the circumference does matter. Okay, now the robot needs to stop at the end, obviously, otherwise it's just going to carry on going. And we know that 1 rotation is 1 circumference. And the part of the robot at the start line. So normally I put, I'll show you just now. I've got another robot. You've got a little, like a marker on the, so you can see exactly where it must go. Okay, so that's what we've observed. I don't know whether you observed it, but that's what we observed. All right, so we make a little boxy here, and it's called listing the variables. We've got a distance that the robot should travel. So we said, just 50 centimeters. We measured the circumference of the wheel, and it was exactly 17.8 centimeters. Now we can calculate. So if we've got to go this long in increments of this much, okay, we're going 50 centimeters in increments of 17.8. So we divide, okay, because then your distance, your circumference multiplied by whatever should give you the total distance traveled. Anyway. Okay, so we've got circumference times rotations gives you distance. Well, that we know. And then we swing it over to the other side, and we say R is equal to D over C, which is 2.81. So we've got to do 2.81 rotations. Great stuff. Okay, so there we go. Oh, no, that's in. All right, so we go. I must actually make a video of this. I must just remember. We must make a robot. Okay, so it travels. It starts at start. It travels 2.81 rotations, and then it stops, and it'll be ching exactly where it has to be. All right. Okay, well done. All right. Hopefully you'll have some more interaction now. Okay, so now we've got this little old robot, and it's got to travel the distance. Okay, so now we're adding something. So now we've got distance and time. Now we're going to add speed. We're going to go faster. And we've got power. Okay. So your power, hopefully we've all got driver's licenses. So if you put your foot down on the power and you're going to go faster, what is it going to impact when you travel the distance? Okay, so we have in our heads, we have some observations that we have observed, that if we put more power, we would think that the time decreases. Oh, good observation. All right. So this is more high school, and this kind of touches on, I think it's grade 10. It could be grade 10, acceleration and deceleration. So you're probably, for those of you who are teaching high school, you'll probably start, okay, we've got to introduce this. So there's almost like a primary school version to explain it, and then the high school version with acceleration. So then we usually put the distance, and we see when to the distance, and we have a run up kind of thing. So that's acceleration, then we start, and then we stop, and then we decelerate. So we'll have 2 different setups. But what we do have is, remember here we said 4 power levels. So we're going to change the power levels. Okay, so we're going to, we think, okay, this is what we have in our head. Speed increases with power level. Oh, my word. Okay, so that's what we have. And then we said a distance long enough. All right. So now again, we make our little table, and it doesn't have to be all nice and neat, and you can draw it all in colors if you want to, which I just enjoy. And all right, so we've got a distance of 1.5 meters, which is centimeters. Now here's one thing that the older kids will know. So if that is centimeters, then that must also be centimeters. Okay, so then we can calculate how many rotations there are. Ting, ting, ting. Then we're going to run it at different power levels. So at 10% power, 20% power. And then we're going to measure the time it takes to get from here to here. All right, now in your head, you've got distance and you've got time that you measured. And we can calculate speed. All right. Okay, so we've got some ting, ting, ting maths here. So we know we've got to do 8.43 rotations, that we know. And we know that distance is speed times time. So if we want the speed, we take distance, which is fixed, and time, which we measure on our, well, not many people measure on this on their watches anymore. You can see how old I am. I think most of the kids measure on their cell phones. Okay, all right. So now we've got a little table here, and we say, okay, power level 10, how long did it take to go from start to finish? And you write it down here, and I think I need to do this experiment. So then we get a speed, right, or velocity, and then we can carry on, and you'll notice that when power level increases, speed will increase, okay, because the time that it takes will decrease. All right, so you can see I've got a really cool book which I'm very keen to do, problem solving with physics, and so hopefully by October we will have some time to do some projects, and I'm looking for some contributors to help me with videos and things, so that'll be really cool. Okay, all right, so where does this all fit into robotics? So first of all, kind of let me start. Normally what we really encourage learners to do is there needs to be some focus or some goal to work towards, and so we really encourage learners or teams of learners to participate in robotics competitions. In that case, like there's two competitions that so if you think of the World Robot Olympiad, then it is a whole lot of linked problems that you have to solve from the one to the other. With first robotics challenge or first Lego League challenge, there's a whole lot of missions, and the teams must choose which missions they're going to do. So they kind of choose which problems they're going to solve. In the virtual gear challenge, again, you can choose which challenges you want to complete. Okay, but in all cases, you'll take each mission and you'll say, where do I start? Where do I end? What do I have to do? How am I going to do it? What do I need to build? What do I need to program? Okay, we'll do this in M3 a little bit more. So I know we're just touching the surface, but we'll definitely unpack that in M3. All right, building instructions. There are enough building instructions to go around, and if you're stuck, I really want you to reach out to us. We've got building instructions and we can help you on that. Programming examples are a good way to start. And I know, especially with Spike Prime, there are a lot of new videos out. I haven't seen them all, but I know there's a kind of a whole collection that's just come out. So look at them, but that doesn't mean that theirs is the only correct answer. If you want to try something and you want to see whether it works, please try it. And if it doesn't work, you're welcome to contact us. Okay. Yeah, so online tutorials are great. I'm not always sure that they are relevant though. So if it's not exactly what you want, you must also just let us know. We were looking towards expanding the program so that we can address specific issues. The danger, however, with YouTube videos is they are wow. And so I'm cautioning you not to show your learners too much of the YouTube videos, because they might get discouraged. Although on the other hand, it might motivate them to learn. And I know the teams in the Northern Cape are phenomenal attachment builders. They have the most amazing designs. They started out looking at YouTube videos and trying to learn from that. And so they have, over the years, each team has mentored the next team. And so we have really amazing attachment builders there. And that is, they can attribute that to learning from YouTube. Okay. All right. Remember I said to you in the beginning, robotics is used to teach problem solving. So there are a couple of reports here, and maybe if you want to, if you've got nothing to do and you want to read it up, maybe think, well, this is relevant. I'm very keen to start writing about our South African experience. And so if you want to chat with me, you are more than welcome. But I do think the development of problem solving skills as we move forward, not over for the fourth industrial revolution, but we're going forth into the fifth industrial revolution, our learners need to have problem solving skills. It's just what they need. All right. And so this is now for you as the coach. So what's going to happen in class, you as the coach are going to be required to understand what's wrong. And there are some classic examples of what goes wrong. And so my classic example, wrong port. You put the wires in the wrong port and the port does not correspond to the program. So also watch some of these problem solving on the robot. I know Mr. Hino has got some really classic ones. And you think it's not going to happen in class. It does. It does. It does. It happens to the best of us. And with my team, it even happened in the competition. And luckily, my team were mature enough to say, it's a problem. We'll just change it. All right. But yeah, to understand, to unpack how the problem must be solved. All right. So we're back to Unit 3's activities. And here, this is where, if I give you a robot now, how would you program the robot to draw the first letter of your name? How would you program the robot to move in a square around a square shoebox? Or how would you program the robot to move in a rectangular shape around a rectangular shoebox? And then how must the robot move in a circle around a bucket? Well, a bucket is round usually. Okay, so I'm going to open that for discussion now. All right. Anybody want to unmute and share something? Okay, no problem. Okay, just don't want you to waste bandwidth. No problem. Okay, so anybody understand what is it? How are we going to solve problems? So let's take any letter. How would you draw a letter T? Well, T, I've told you what the answer is. All right. So with the robot, you need to be able to solve the problem. You need to be able to write the computer program. Is there anybody who has not yet installed EV3 class pack or no? Classroom, EV3 Classroom and or Spike Prime. So everybody has the software then. Okay. Yes? All right. So everybody has the software. So when you are designing your software or writing your computer program, you must always have in mind, what are you trying to solve? And it's also not good to just solve it and think, okay, how am I going to solve this problem? I really recommend that you sit as a group and you work out together how to solve the problem. How would you solve the problem? Okay, so let's do, how do you get a robot to move around a square? Anybody? How would your robot move in a square? Anybody want to unmute? See, I've got another Sabia in the meeting. Hello. No? Okay, so, but you're welcome to interrupt as we go along. So if you're going to program the robot to go in a square, you need to find the length of your square, of your box. Okay, so you'll take the box and find out what the length is. Say the length is 6 centimeters. Then the robot must go around the box. So it must go forward and then it must stop. All right. So here's your robot, ping, ching, ching. It goes forward and then it stops. Now it's got to go around the corner. Okay. How does it go around the corner? It goes around the corner by not using this motor. So only using the outside motor, because if you turn that, then it turns like that. Okay. You must just check which, I think for this robot with the weight that it has and the wheels that it has, it needs about 2.2 rotations. Okay. It turns. All right. Now it's on this side of the box. Now it's got to travel again, your 6 centimeters, then it has to stop. Then again, we put this motor off and we use this motor. Then we rotate this motor 2.2 rotations and it turns like that. There we go. Now it goes further on, ting, ting, ting. Comes to the corner. You know what it's going to do. Hey, yes. Stop. Do 2.2 rotations on the one wheel, on the C wheel, and then go back. All right. So step by step, when you're solving problems with a robot, it's step by step by step. Okay. So now if you've got a robot, you want it to go around, say, in a circle around a bucket. Okay. Yes, you can get the clever kids that want to go with a in a square around, because initially I just said, how do you go around the bucket? So then The clever learners just said, oh, well, we'll just use the same program. We go a square around the bucket. No, I actually didn't want that. I wanted them to know how you can go around, but in a circular motion. So if you're going in a circular motion, the inner wheel against the bucket is going with less power than this one. All right. And so you'll go around like that. Okay. And so it goes around the bucket in a circular motion. And it makes it more fun if you then attach a Koki pen to it. And then you see the path that the robot moves. It's understanding how to solve a problem. Okay. You'll also see it tomorrow in the next lesson. When you look at a problem, look at the verb. Okay. So the verb is always, what do we have to do? So this is just drive around. So we drive around a square or a rectangle or a circle. The first one that you have to do is go here and go there. Okay. The quickest way to get learners to understand that is to have a slab of chocolate or have a packet of sweets or something. So, okay, you've got to go there, fetch it and come back, or there, drop it and come back. So the here and there is a very good learning place or learning environment. And with that said, I think we do need to do some practical. So when we have a practical session in the hub again, we'll have some robots being demonstrated, and then you can see. We should have taken videos. I'm just looking, Ansani, we should have taken some videos when we had the practical workshops in the holidays. Next time, we must just not forget. Next time we'll take some videos. Okay. Are there any questions about solving problems? And how do you go about solving problems? Anybody? No? Yes, Thomas. Hi.
Hey, hello everyone.
Hello, Thomas.
Regarding your questions in terms of how to solve the problem, because I don't have the set yet, ne? But what I did,
I like the word yet. I like Thomas. Yeah. I like the word yet. Yes.
Yeah. So what I did, I installed the brick link.
Yes.
So I've been trying to work it out in terms of how to design and everything. But what I'll do regarding your questions, I will answer it a little bit later after I've done to design a little bit, and I'll send it to you.
All right. All right.
So I just want to find from your side, like, is that relevant to use the Brink link to maybe especially to solve the questions and yeah.
Okay. So the brick link is just for design. You're just designing a robot. Okay. There's another really cool little robot that you can work with. I'm going to and it's a funny little robot. It's in GearsBot. Can you see the GearsBot? Can you see the chat?
Let me check on my side. Yes, I can see the chat. Yes.
Okay. So download GearsBot. GearsBot is a free little software that really gives you a good idea of solving the problem. Okay. So you get your robot to move in a square. I see Casper's going to help me out now. You can go in a square, you can go in a circle, but GearsBot, there we go. Oh, I thought that was the GearsBot link. It's okay. With the GearsBot, you can practice your programming with it's a little simulated robot. It doesn't look great, but I think it's a really good way to start getting learners to understand solving problems.
Okay. Yes, it makes sense. So I have to download this software, ne?
It's called GearsBot. You can Google it and then you just download it and install it. It's quick.
It is on the link. It is in the chat now.
Oh, there's the link.
Yes, I got it. Yes, I got it. Yes,
okay.
I got it.
Thank you so much. The cool thing about that is you can program in Scratch. So you program your robot in Scratch, much like what we're busy doing, eh? And it'll also give you the equivalent in Python. And so for that, I'm really impressed with this little software option. Yeah.
Okay, thank you so much. I'll download it and then I'll just try to work out and see.
Okay. All right.
Okay, thank you so much.
Thomas, otherwise, early in September, we're going to have some workshops in the hub, and then you can come and play with the robots. Okay.
Oh yes, that will be lively. Yes, I will.
Okay. And then, well, everybody who can't be there with us in person, we'll just have a really cool, I've got a little camera, and then we will show how we did a hybrid session, and it feels so far away. We did a hybrid session in June, just showing, kind of trying a piece of code and figuring it out, and then showing the hybrid, the virtual people as well. It's just because it's just a bit more interactive as well. Yeah. Okay. Are we good? All right. I want to show you something, but now I'm thinking. So we've got kind of a whole lot of things happening in my head. So the one really amazing thing is, and Anzani, I'm wondering whether you can not share the link to the launch. There is a virtual link to the launch. So the first Lego League competition launched last night, and the challenge is about. Thanks, Anzani. The challenge is about art and science and technology, and how the learners can combine those three. So hectic stuff. So on the one hand, the team of learners need to do a research project. On the other hand, they've got a whole lot of problems they need to solve. And I say problems with a definite, they need to solve the problem, but they can choose which problems they solve. And they get points, their robot gets points according to what problems they solve successfully.